Okay, this is blinking, which means it's recording. Just so that I can check, is there anyone who did not receive the course announcement email that I sent saying that we're meeting at 1 p.m.? Those of you who have been sitting here since 12:30 might be such people. Did everyone get that announcement? Okay. If you did not get that announcement, email me because it means you're not on my email list. Okay. Any other announcements? I don't think I have any other announcements of an administrative nature. I apologize. I understand that even though we moved the class, there's still some people who have course conflicts. As I said, I'm going to do my best to record these, and last year's recorded lectures are also online. So between those, you should have access to all of the information you need should you have to miss a class. And it's sort of unfortunate that the scheduling worked out that way this year, but I think at this point there's not too much that can be done about it. Okay, so unless there are any comments on that scheduling business, perhaps we can continue with the physics. Would you mind closing that? Thank you. So last time we discovered Lagrangian mechanics. So let me just remind you of the Lagrangian recipe for studying a mechanical system. So this is an extremely efficient algorithm for writing down the equations of motion of many, but not all, mechanical systems. And so the basic idea is that you start with a system with some moving parts R alpha. So R is a vector labeling the positions of the different parts of the system. And then you identify some degrees of freedom, qi, where I runs from 1 up to n. And you write the position of every part of the system as a function of these dynamical variables. So here I is an index that runs from 1 to n. Then we compute the kinetic energy as a function of qi dot, and time. We also compute the potential as a function of the QIs, and possibly time, if, for example, we're in some rotating or accelerating coordinate system. And then we define the Lagrangian, which is the difference between the kinetic and the potential energies. And then we have n equations of motion. So remember here, n is the number of degrees of freedom. There is 1 degree of freedom for each qi, I running up from 1 to n. And the equations of motion are the Euler-Lagrange equations. So for each I, we just write down this quantity d by dt, dl by dq dot, minus dl by dq, and set it equal to 0. And these equations of motion are equivalent to the usual Newtonian equations of motion. But are often easier to find using this Lagrangian formalism. And I spent about half of the class last time, a third of the class last time, describing a variety of relatively simple examples of systems which are described by Lagrangians. And I used the Euler-Lagrange equations to write down very quickly and very simply the equations of motion of the system. So your problem set, which is due on Monday, is a little on the long side, but there's a good reason why it's a little on the long side. And the reason why it's long is that I want you to have lots and lots of practice of writing down the Euler-Lagrange equations. I want you to get to the point where you can find Euler-Lagrange equations in your sleep, although hopefully that won't be necessary. And indeed, it is the case that almost all of the systems, mechanical systems that you can think of in your head are described by Lagrangians of one sort or another. The two exceptions, the two cases where one cannot find a simple Lagrangian description, are the case where the constraints are non-holonomic, meaning that it is impossible to do step one of this procedure, writing the positions simply as the functions of the dynamical variables. And the other case when it is impossible to find a Lagrangian is when we have non-conservative forces, in which case it is impossible to do step three and write down a potential. So examples of non-conservative forces include friction forces. Last time I went through three examples. I believe I did a sliding block on an inclined plane, which is allowed to move. I did a bead on a wire, and I probably did a pendulum, because that's my favorite example, because I can almost always remember it without making any mistakes. At this point, we could play a game where I ask you to shout out the name of your favorite mechanical system, and then I will challenge myself to derive its Lagrangian before your very eyes. Shall we play that game? Does anyone have a Lagrangian system whose Lagrangian they would like, a mechanical system whose Lagrangian they would like to compute? Don't give me the double Atwood machine, because I don't even remember what that thing is. It's a bunch of pulleys and weights. I don't remember what it is. Shall we try a double pendulum? I can usually get that one right too. Or we could continue. You guys are not very enthusiastic. It's right after lunch. Your blood sugar levels have probably dropped, and you're entering comas. What's that? A rocket. Okay. Well, so if you really want to study a rocket, of course, the mass of the rocket is a function of time. There's nothing wrong with that. So let's consider a system whose mass depends on time. This is a nice example of a system which is not invariant under time translations. So let's imagine we have an object moving in a gravitational field. So let's call the position of the object x, y, or let's just talk about the vertical position. So we have an object whose vertical position is y, and so the kinetic energy of the particle will be 1/2 m y dot squared, and the potential energy of the particle will be mg y. But you could certainly imagine situations where the mass of the particle depends on time. So the Lagrangian will be 1/2 m y dot squared minus mg y. Yes. Did I make a mistake?
The dot and the y?
Oh, the dot is a time derivative. So dot is d by dt.
No, I mean like beside the t.
The dot on the y. Oh, this is the mass. Sorry. I'm not a very good artist. I can't even draw a point well enough that anyone can understand what it is. So this is an object of mass m, and y is the vertical position of the object. And we could imagine, for example, that, this is some asteroid that is heading towards the Earth, but as it heads towards the Earth, it's disintegrating and losing mass in some way. Or the gases coming out of the asteroid are making its mass decrease. And then the Lagrangian would be exactly as you think it is, except the mass would be some explicit function of time. Now, more interesting would be the case where the mass is a function of position. So the mass could also be a function of position and time. Or it could be a function, if we could have some horizontal direction x, and it could be a function of x as well as y. And in all of these cases, one just has to follow one's nose and compute the Euler-Lagrange equations in the manner that I described above, and you will continue to have the correct equations of motion. Yes, there was a question.
What kind of physical processes where the mass depends on position?
Well, let's imagine that we have a particle in a potential, but the potential is a more complicated function than just the constant gravitational potential that I've described above. For example, let's imagine that I'm in a gravitational field, and I want to consider the case where I'm not using the approximation where the gravitational force is constant. I want the gravitational force to depend on where I am. So, for example, we will spend a lot of time studying the motion of objects in the solar system and solving quite explicitly the two-body problem. That is a case where you have a potential that's a very complicated function of position. And so anything like that would be a case where effectively the mass, by which I mean the gravitational potential, is a function of position. People don't talk about it as often, but of course there are also cases where the potential is a function of time. So we usually don't see that very often when solving problems in gravitational physics, although of course one can consider them and they're important, but you very often see them in problems involving electromagnetism. So for example, perhaps on this problem set, perhaps on a future problem set, you will write down the Lagrangian of a charged particle moving in the presence of an electromagnetic field. And as you probably did not learn in your electrostatics class, but probably will learn in your electromagnetic waves class, it is very common to talk about configurations where the electromagnetic fields are functions of time. These are called light waves. And so if you want to study the motion of a charged particle as some photon passes by it or as some light wave passes by it, that effectively means that the potential felt by this will depend on time. So it's a quite common occurrence. Other questions? Yes?
Why would the Euler-Lagrange equation still hold when the mass is a function of time? Because when you derive it, you take total derivative of describes the time of the Lagrangian. Now, something like this term of...
Yes, and at each point along the way, I allowed the various terms in the Lagrangian to have some explicit dependence on time. I demanded only that the force was conservative, not that it was time independent.
So now you demand that you know mass as a function of time before you do it.
Yeah, let's say we know them. Yeah. You could also imagine that the mass is some much more complicated function of other things, like it could depend on the whole history of the universe. In that case, I don't know if there would be a conservative force in a Lagrangian description. Probably not. Yes?
If you imagine a system as being accelerated by some kind of processes, and so the energy increases but in the time,
Yes.
Can you describe the system equally as a mass that changes in time? Is it
Yes.
the equivalence between mass and energy?
Yes. So for example, a very simple, so for example, if I'm continuously pumping energy into a system or removing energy from a system, then that's effectively like the mass changing as a function of time. And this happens all the time in physics. So for example, later on we'll describe oscillators. We're often used to driving oscillators with some external force. And a mass that's a function of time could just be useful if we're describing the behavior of the system in terms of some external driving force. Okay. So we have learned as well last class that not only is the Lagrangian formulation practically useful because it allows you to write down equations of motion in a very quick an easy-to-remember way. It is also conceptually useful. And I went through the definition of the Hamiltonian at the end of class last time. I went through it a little quickly, so let me just remind you. So we define the Hamiltonian of a system to be the sum on I, q I dot, dl by dq dot. And then we subtract off the Lagrangian. And this is useful because if you compute the time derivative of the Hamiltonian, then the total time derivative of the Hamiltonian, including all of the implicit dependence of the Hamiltonian, of the QIs on time, so that total time dependence of the Hamiltonian is equal to the explicit time dependence of the Lagrangian on time. Do you guys remember the derivation? I went through it last time, so if you don't remember it, I'll let you go through the notes again. Was there? Yes, there was a minus sign. Thank you. So what that means is that if we are in a case where the Lagrangian is independent of time, or more specifically, if the only dependence of the Lagrangian on time is implicitly through the variables qi, then that means that the Hamiltonian is a constant. It depends only on the solution to the equations of motion, but not on anything else. And in particular, it does not depend on time. And indeed, in many cases, the Hamiltonian is just the sum of the kinetic and potential energies, and so it is just the total energy. And as I began to describe at the end of class last time, this is an example of Noether's theorem. A topic which is one of the most elegant results in theoretical physics and in experimental physics, and one that we will return to again and again throughout this class. And so in particular, it means that if we have a time translation symmetry, we have a conserved energy. So examples of systems where we do not have a conserved energy would include those systems where we have some sort of external driving force of the sort that we were discussing a few minutes ago. For example, if I take an oscillator and I have some driving force that is continually pumping energy into the system, then you will discover naturally that energy is not conserved because the oscillator is continually increasing its energy by absorbing that of the external driving force. And indeed, if you write down the Lagrangian for such a system, as we will do later on, you will see that it has some explicit time dependence. Alternatively, if we go up to the example that I considered before, where the mass is a function of time, then again, that will have an explicit time dependence, and so there will not be a conserved energy. Are there any questions on this before I continue? Okay, so there's another example of Noether's theorem, which you also already are quite familiar with, although you probably don't know that it's an example of Noether's theorem. So let's imagine we have some dynamical system which is given by some dynamical variables qi and a Lagrangian, which in general will be a function of qi dot, as well as time. And let's imagine that this Lagrangian is independent of Qi. Although, even though it's independent of Qi, it could depend on Qi dot. So if the Lagrangian is a function only of Q dot n time, then the Euler-Lagrange equations will be the statement that d by dt, so what are the Euler-Lagrange equations? There's one term that says d by dt of dl by dqi dot, and then we subtract dl by dq and set that equal to 0. So dl by dq is now 0. So this is 0. So that means that we have discovered another constant of motion. So that implies that dl by dqi dot is a constant. We have a name for dl by dqi dot, and that name is momentum. So the momentum, often called pi, conjugate to qi, is defined as the derivative of Lagrangian with respect to qi dot. So this is the definition of the momentum conjugate to one of our dynamical variables qi. And this momentum is conserved if L is independent of qi dot, of qi. So I have used a slightly odd language here where I have talked about the momentum conjugate to a dynamical variable. That's because this notion of momentum is a generalization of the notions of momentum that you have encountered so far in your physics education. So simple examples of momenta would be the following. So let's imagine we have a free particle moving in the xy plane. Thank you. Oh, bye. I thought he was closing the door there. So if we have a free particle moving in the xy plane, then there is no potential. The Lagrangian is equal to the kinetic energy, which is 1/2 m x dot squared plus y dot squared. And that is independent of x and y, and depends only on x dot and y dot. So the momentum conjugate to the variable x is the derivative of the Lagrangian with respect to x dot, which is mx dot. And in your U1 or U0 physics classes, you had a name for mx dot. It is the mass times the component of the velocity in the x direction, otherwise known as the linear momentum in the x direction. Likewise, the momentum conjugate to y, my dot, is the linear momentum in the y direction. And we see that whenever the system that we are considering is independent of translations in x and y, we have a conserved momentum. There's a second example of momentum that you have encountered. So let's consider, for example, a particle or an object moving on a circle. I tend to use the word particle a lot only because I'm trying to contrast it with extended objects and rigid bodies that we'll be studying later on in the course. So let's imagine we have an object moving on a circle, and let's parameterize the dynamics by the angle that the object makes with vertical. So what is the Lagrangian? So the x position will be r times cosine theta. The y position will be r times sine theta. With that definition of theta, with those equations, I'm using the other polar coordinates where I measure the angle off of the horizontal axis rather than the vertical axis. Of course, you can use whatever theta you like as long as you're consistent. If you're bored, I recommend that you work it out with some other angle theta definition in your notes. So with this definition, the Lagrangian will be equal to the kinetic energy 1/2 m x dot squared plus r dot squared. What is x dot? Well, x dot will be r minus r sine theta theta dot, and y dot will be r cosine theta theta dot by the chain rule. So the kinetic energy 1/2 m x dot squared plus y dot squared will be 1/2 m r squared times sine squared theta theta dot squared plus cosine squared theta theta dot squared, which is theta dot squared. And this is independent of theta. So because the Lagrangian is independent of theta, I can define the momentum conjugate to theta, which we would usually call p theta. That's the derivative of the Lagrangian with respect to theta dot, which is m r squared theta dot. And you had a name for this momentum in your previous mechanics classes, and that would have been angular momentum. And we see that for any system which is rotationally invariant, in the sense that the Lagrangian does not depend on the angle theta, angular momentum will be conserved. So just to summarize, a linear translation symmetry will lead to a conserved linear momentum. An angular translation symmetry, or I guess we would call it a rotation symmetry, will lead to a conserved angular momentum. And finally, a time translation symmetry will lead to a conserved energy. So these are the three famous examples of Noether's theorem in classical mechanical systems. Although throughout this course we will encounter various other versions of Noether's theorem with more interesting conserved quantities. In fact, we could now play another game where you shout out your favorite symmetry and then I respond with the associated conserved quantity. Or we could play the other game where you shout out your favorite conserved quantity and I respond with a symmetry. Shall we play that game? It's a fun game. Or we could play that game later when we do a more systematic treatment of Noether's theorem. Maybe we should do it later so that you have something to look forward to. Unless someone has something they're just dying to know right now. Yes?
Charge conservation.
Charge is a conserved quantity. It is associated with a symmetry known as gauge invariance. You may have encountered gauge invariance in your electromagnetism classes. So you know what an electrostatic potential is, V. If you shift v by a constant, nothing changes. In the same way that if you shift time by a constant, the laws of physics are the same. Shift v by a constant, the electric field is the derivative of v, will not change. And so that is a symmetry known as gauge invariance. The term gauge invariance is a little Baroque sounding. It comes from, it has a sort of weird history, but it's known as gauge invariance, and that is the symmetry that leads to charge conservation. There's a similar symmetry for magnetic fields, which leads to current conservation. Yes?
What about like information conservation?
Yeah, that's a good one. Yeah, I don't have a good answer for that one. It's true that information is conserved in a sense. Well, in thermodynamic systems, information is not conserved because entropy if entropy is constant, then if you have an adiabatic system where entropy is constant, then information is conserved. But of course, the second law of thermodynamics says that entropy is not necessarily constant, but rather it is a monotonically increasing function. So in a thermodynamic system, information is not conserved. In quantum mechanics, however, there is a version which is probability that is conserved. There's a current associated with probability the same way that there's a current associated with electromagnetic charge. It's difficult for me to, I don't know quite exactly what the right symmetry is to associate with that. Good question. Okay, your job is to find out and tell us next time. Any other questions? You see how this goes. That's a good one. Yeah. No other questions? There must be some sort of way of thinking of what there must be some way of thinking of the symmetry associated with. Okay, well, let's not get distracted by that, although that would be fun. Okay, any other questions, perhaps of a less conceptual nature? Okay. So we have now met Lagrangians, and we have learned that the Lagrangian formulation of mechanics is an extremely efficient way of organizing the equations of motion of a general dynamical system. But, in fact, we can do better. So, in fact, there is a much cleaner conceptual repackaging of the Lagrangian formulation of mechanics, which goes under the name of the action principle, or Hamilton's principle. As you'll discover, a lot of things are named after Hamilton in this subject. So I should probably start out with a bit of words of philosophy. So far, our derivation of Lagrangian mechanics has been correct, but it has been a little ad hoc. I sort of defined for you the notion of a general dynamical variable, and then by trial and error or by fiat, I wrote down an efficient way of encoding the equations of motion into a function that I call the Lagrangian. But I did not give you any conceptual understanding of why the Lagrangian is the right thing to consider, nor what role it plays in physics. And so that is what I would like to do now. So let me start by reminding you of something that you already know. So I will remind you of Fermat's principle. So this is something that you may have learned in your optics class, or the optics section of your elementary physics classes. And that is simply the statement that light rays travel along paths, along the shortest path between 2 points. More precisely, if you have a point here and a point there, then light could, in principle, in some strange universe, travel along any curve that connected the 2 points. However, light, in fact, in our world, travels along the shortest distance, the line which is the shortest distance between the 2 points. Which means that if I define the length of a curve, so let's say that I have a curve which is parameterized by two functions, x of s and y of s, where s is a parameter which continuously labels different points along the curve, then the length of the curve, L, is just the integral ds of the square root dx by ds squared plus dy by ds squared. So that is the formula for the length of a curve, which hopefully you have encountered in your multivariable calculus classes. And, yes?
What do you mean by light will choose to take the shortest path? Because it's going to be emitted in all directions, and it just happens that the ray that's emitted in that direction will hit that point.
Yes, but the light ray connecting any 2 points will travel along a straight line. If you have a light bulb over there, and I am observing it over here, the light that I see traveled in the straight line between your light bulb and my eyes. Of course, if I were in a different position, I would have seen a different light ray, but that light ray will have still traveled on a straight line. That's what I mean. Yes. Yes. No. Was there a question? No. Okay. So for any curve that connects these 2 points, I can define the length of the curve by integrating the arc length along the curve. And this length will be minimized for the trajectory of that light will take between the 2 points. So in optics, one, for example, uses this principle to determine the angle of reflection of light off of a mirror. It shows you that light is reflected at the same angle. The reflection angle is the same as the incident angle for light, which is bouncing off of a mirror. So let's ask the following question. Does every mechanical system obey a minimization principle of this sort? For example, if I wish to study the motion of this thermos as I hurl it against the wall, is that thermos traveling on a path which minimizes something? If it's true, then that would be a rather remarkable fact, because depending on the force with which I hurl the thermos, it may travel on a curved path, which is clearly not the shortest path connecting 2 points. But is it possible to write down the dynamics of the thermos moving through this room in a way which is a minimization principle, in the same way that Fermat realized that the motion of light can be described by a minimization principle? And the answer to this question is yes. I wouldn't have asked it if the answer were no. And indeed, it turns out that this answer is very closely related to the Lagrangians that we discovered last week. So, in order to understand this minimization principle, which goes under the name of the action principle, let's imagine the following. So, consider the set of all possible paths qi of t that a system could take through configuration space. So in particular, we have some set of dynamical variables qi. There are n of them. So in my mind, I could think of them as describing some space, which is the space of all configurations of the system. And then I could imagine that the system takes some path through this configuration space as a function of time. So in particular, we know that a system will actually take one very particular path through configuration space, namely the one which solves the equations of motion. But let us just think for the moment of all possible paths that the system could take through configuration space. And then define the following. For a given such path, define the action, which we usually denote by the letter S, that is a function of the path, and it is defined as follows. So, it is the integral dt of the Lagrangian as a function of qi and qi dot evaluated on that path. So qi and qi dot are for whatever path I am considering. And L here is the Lagrangian. And in general, we will take a path which starts at a particular time t initial, so we'll integrate from t initial, up to some final time t final. And this is the action of a path qi as a function of t. So just as for any 2 points in space, I imagined a curve connecting them and took the length of the curve to be the integral of the arc length along that curve. I now imagine in my head some abstract space of all possible configurations that the system can take. And if I have some initial configuration and some final configuration, then I could imagine some path that the system takes through configuration space, connecting these initial and final configurations as a function of time. So this here is configuration space. Which you should think of as the space of all QIs. And this here is the initial QI, so QI of T initial. And that point here is QI of T final. I should make an important point here, which is that this action is not a function of points on configuration space. It is not a function of QI, but it is a function of paths through configuration space. So it depends on the QIs as a function of T. it is not a function of a single variable, but rather a function of a function. In the same way that the length of a curve is not a function of a point, but it is a function of the shape of the curve. And the claim is the following. The path through configuration space that a mechanical system takes minimizes the action as a function of the path. So this is the statement that if I imagined all possible trajectories that this thermos could take, which connect it from my hand to that wall over there, I could imagine any trajectory. I could imagine it zooming off all around the island of Montreal before hitting that wall over there. And the actual physical path which is taken by the thermos is the one which minimizes not the distance between those 2 points, but rather the action, which is defined as the integral of the Lagrangian of the thermos. So I should mention a couple technicalities here, which is that technically the path does not minimize the action, but rather it only extremizes the action. So we often call this the least action principle in analogy with Fermat's principle. But in fact, it is not actually a minimum of the action, but only an extremum. And moreover, it is not a global extremum, so it's not a global minimum or a global maximum, but in fact only a local extremum. So despite that, this is often referred to as the least action principle. Or alternatively, as Hamilton's principle. So what I would like to do for you now, probably starting today and then finishing next class, is explain to you exactly why it is that a system will take a path which minimizes the action. But I should start probably with a few general remarks, which is the following. So S as a function of paths is not a function of a single variable, but rather is a function of a function. In the same way that the length of a curve is a function of the shape of the curve, which is a set of two continuous variables, rather than a function of a point. And so there is a name that we give functions of functions, and we call them functionals. It's not a particularly good name, but it is the name that has stuck. And we have a particular notation that we use for functionals, which I have already used, which is that we use square brackets to denote the dependence of a functional on a function, rather than curved brackets. To denote dependence on a function. So that is just a bit of notation, but it is useful because it helps us keep in mind the fact that the action is not a function of qi it's not a function of n degrees of freedom, but rather as a function of n functions of t. So what we now need to do is minimize the action with respect to these n functions q of t. And to do that, we will need a little bit of new mathematics. We will need what is known as the calculus of variations. So why do we need a new piece of mathematics? Well, the reason why we need new mathematics is that we are used in single variable calculus, or even in multivariable calculus, to computing or to minimizing a function of. We're used to minimizing a function of one variable, or perhaps n variables. To minimize a function of one variable, you set its derivative to be equal to 0, and then you take the points where that derivative is equal to 0, and if you are very diligent, perhaps you even do the second derivative test to check whether you have a minimum or a maximum. Likewise, if you have a function of n variables, you calculate the gradient, and you set it equal to 0, and then perhaps you do a second derivative test by computing the Hessian matrix. But now we have a function which depends on another function rather than on some finite number of variables. So we need to understand how to minimize a functional, which, if you want to, you could think of a functional as a function of an infinite number of variables. Why is that? Well, a functional such as the action S depends on q of t. Let's just consider one degree of freedom for the moment. But q of t is itself a function which I could think of as an infinite set of parameters, or an infinite set of variables. So what we need to do now is understand how to do calculus with an infinite number of variables. So, in fact, I will not teach you all of calculus with an infinite number of variables. I will only teach you half of calculus with an infinite number of variables. So calculus, as you remember, is divided into two parts. There is differentiation and there is integration. It turns out that all we need to do to compute minimas is understand how to take derivatives of an infinite number of variables. Taking integrals over spaces of functions is much more difficult and is outside the scope of this class. There is a sense in which classical mechanics is the theory of functional derivatives and quantum mechanics is the theory of functional integrals. So if you wish to learn how to integrate an infinite number of functions, I suggest you ask your quantum mechanics teacher. Although I probably won't be able to resist mentioning a few words about it later on in this course. So what I would like to do now is discuss the general problem and begin to demonstrate for you how one minimizes functions of an infinite number of variables. Before I do so, are there any questions? Silence. No questions? Okay. So let's consider the following general problem. So let's imagine that I have a function that I'll call capital F that depends on y, which is itself a function of x, the first derivative of y with respect to x, as well as x. So this will just be a normal function, not a functional. It'll depend on the value. It'll essentially be a function of y and x, and I will just take x to depend implicitly on, I'll take y to depend implicitly on x. And then we will define the functional that I will call I, which is now a function of the curve y of x, which will be the integral between some initial and final values of x of f evaluated on y. So here, y is a function of x, which is defined on the domain where x runs between x0 and x1. So you can see that this problem that I have written up here is exactly the same problem as the minimization of an action. I have just replaced t by x, q by y, f by l, and I by s, because I like torturing you. No, I have done that because, in fact, action principles are very useful. The calculus of variations is very useful. And I want you to keep in mind that the techniques that I am presenting are, in fact, more widely applicable than just to mechanics problems where I am minimizing an action. Indeed, many of the very first problems which led Newton and friends to develop calculus were problems involving the calculus of variations. So then the question we ask is what y of x extremizes this functional. So before solving this problem for you, I would like you to just remind you of how the problem works when we have one degree of freedom rather than an infinite number of degrees of freedom. So if we have a function of a single variable, so here y will just denote a single variable, and I will just be some function of y, then the extremum is at the value of y where the derivative of I with respect to y vanishes. So physically or geometrically, how do you think about that statement? The way that you think about this statement is that if we were to deform y by a little bit, so let's say you start with some initial value of y, and you add to it a small variation that I could call delta y, then I, at this new point, y plus delta y, well, we compute that just by Taylor expanding, because I imagine that this variation is very small. So it'll just be I of y plus di by dy, evaluated at this point y, times delta y, plus terms that are of order delta y squared. And so the minimum, or the extremum, is the value of y where the term in the variation which is linear in delta y vanishes. So this is a completely intuitive statement, which is the following. If you're at an extremum of a function, a minimum or a maximum of a function, then if one varies the position, if you vary a little bit around that extremum, then the term in the function which is linear in that variation will vanish. That's just the first derivative, which vanishes at a minimum. Yes?
Did you assume that the derivative of I exists in the whole domain?
Yes.
In the domain?
Yeah. I'm going to be play a little. I'm not. This is not a math class, so I'm not going to use epsilons and deltas and be precise about functions that are continuous and differentiable and smooth and complex and analytic and holomorphic and all of those things. So we will just yes. So I am assuming all of those wonderful things. Any other questions? Okay. So what I would now like to do is apply the identical principle in order to minimize a function of an infinite number of variables. So let's apply the same principle. So in particular, the first thing that we do is we imagine we now have a function y. So this is y as a function of x. And so y is a function, so if this is x naught and this is x1, then y will be some function between 2 points, y of x naught and y of x1. So the first thing that we do is we fix the values of y at its endpoints, so y at x naught and y of x1. And then we imagine we consider a curve y of x connecting these endpoints. And then we imagine varying that curve slightly. So we will perturb the curve a little bit by deforming y of x to y of x plus delta y of x, where delta y of x is now a function which is the small perturbation around our curve y of x. So technically speaking, I should take it to be an infinitesimal variation, but I will not hold fast to epsilons and deltas and such things in this course. So then what we want to do is compute the variation, which I could call delta I under this perturbation, and demand that the term which is linear in delta y will vanish. And finally, I should point out that since we've fixed the endpoints, let's just set the variation of y at the endpoints to be equal to 0. In particular, what we want to do is we want to vary only over those curves which have fixed endpoints. So the perturbation will be taken to vanish at those endpoints. So are there any questions on our strategy before I do the computation. We are just doing the same thing that one would do if one were trying to minimize a function of a single variable. You vary that function slightly, and you look at the place where the linear part of the variation vanishes. So let's do that. So I, as a function of y of x, was defined to be the integral of f evaluated at y of x, y prime of x, or dy by dx, and x, integrated between x0 and x1. So what I now want to compute is how this thing varies when I vary my function y of x a little bit. So I want to compute this functional I at y of x plus delta y of x, and I want to subtract off the value at y of x. And I'm only going to work to linear order in this variation delta y. So what is this? This is the integral of f at y plus delta y, y prime plus delta y prime, and x, minus f at y, y prime, and x. I should note something which sometimes confuses people the first time that they see this, which is that the variation of y prime is the variation of y prime. Okay, let me be a little more specific. Under y goes to y plus delta y, y prime goes to y prime plus delta y prime. So that means that the variation of y prime, the variation of y prime is the variation of y prime, if you see what I mean. If you ask how y prime varies, then it is the variation of y prime is the variation of y prime. So you need to be careful about your comma placement there. This is one thing that sometimes confuses people the first time they see it. So I just want to bring that up, because sometimes people ask me why I just get to put the derivative of the variation of y right there. Okay. So now if we want to compute this variation, we just go ahead and Taylor expand every term in sight to first order in delta y. So the variation in I, which was the difference between I at y plus delta y and I at y, will be equal to the integral from x0 to x1 dx. Well, the first term comes from Taylor expanding this guy right here. So we have df by dy times delta y, plus terms which are higher order in delta y, which we will neglect here. The next term will be df by dy prime times delta y prime, and that's it. Is that clear? All I've done is Taylor expanded that expression on the top line to first order in delta y, to first order in the small variation. Now, I would like to do, yes, there's a question? No question. Now, I would like to do the following sneaky trick. So watch closely. There is nothing up my sleeve. What I would like to do is take that second term and integrate it by parts. So when we integrate that term by parts, we get, well, there's the first term, nothing of which happens to it. And then we have minus d by dx, df by dy prime. That comes from integrating this guy by parts. And then we have a boundary term. So plus the integral of the total derivative of df by dy prime delta y. And that guy, of course, is just equal to df by dy prime delta y evaluated at x1 minus the same thing evaluated at x0. And now we use the fact that delta y at x0 and delta y at x1 are equal to 0. So this boundary term vanishes. Oh, I'm sorry. I forgot. Someone should have reminded me. I forgot a delta y there. Sorry about that. Is that clear? All I've done is integrated by parts. And I've used the fact that our boundary conditions are such that the boundary term that arises when I integrate by parts vanishes. So just to summarize, the variation on I to first order in the variation of y is the integral of x from x0 to x1 of df by dy minus d by dx df by dy prime times delta y. Are there any questions on that derivation? This is one of those things that you just sort of have to sit through and do yourself before you really believe it. I have the problem that I have done it myself many times, and so I really believe it. So perhaps I don't see the conceptual difficulties that you fellows, ladies and gentlemen, might be seeing right now. If you are confused, I recommend that you do go through it and check it for yourselves. Now, this has to vanish. And in particular, this should vanish for arbitrary delta y as a function of x. And delta I is the integral of the product of two terms. The first term there in the curly braces times delta y. And it needs to vanish for any delta y. Delta y is a function. It has to vanish for every delta y. So that means that y of x is a path which extremizes the functional I as a function of y of x only if the quantity in the curly braces vanishes. So this equation that I've written here, which is the condition that the functional I is extremized, may look familiar to you. Perhaps it will look even more familiar to you when I tell you its name. So this equation is known as the Euler-Lagrange equation. That is the same name that I gave to the equation of motion in the Lagrangian formulation, and that is not an accident. This equation has another name. So the quantity which appears on the left-hand side of this equation, which is df by dy minus d by dx df by dy prime, has a special name. It is called the functional derivative of I with respect to y. And it has a special symbol where we write di by dy, but to remind ourselves that we are considering functionals rather than just functions, we write them using Greek d's instead of, so little deltas instead of just the usual di by dy. And so this is known as the functional derivative. And it is the functional derivative of I with respect to y. And often I will be careful about writing y of x there to accentuate the fact that I is a functional that depends on curves y of x rather than just numbers y. Questions? Okay. So let's now ask the following question. So what if we have a functional of n functions? Rather than just one function. So I could imagine that I have a functional, I, that depends on some collection of functions, yi of x, where I runs from 1 up to n. And this functional is defined to be the integral dx of some function f that depends on the yi's, their first derivatives, as well as x. So we can then go ahead and repeat the reasoning that I went through before. So the variation of I under a small variation of the yi's, so now we're varying n functions yi by some small variations delta yi. So the variation of this functional I is the integral dx f at yi plus delta yi and yi prime plus delta yi prime and x minus the same thing at yi prime and x. And then we expand this to first order in the variations delta yi, and we do this just by using Taylor's theorem. So now we have the variation coming from the dependence of f on y, which will now be a sum on I, f of df by dy I times delta yi. So that's just Taylor's theorem in n dimensions rather than Taylor's theorem in one dimension. And the second term will involve the sum on I, the derivative of f with respect to yi prime times delta yi prime. And I can now go ahead and use the same trick by integrating this term by parts and noting that it is equal to minus the derivative with respect to x, df by dy I prime times delta yi plus terms which are boundary terms that vanish when I consider boundary conditions that are fixed, just as they did in the single variable case. So we conclude that the variation of I is the sum on I, integral dx, df by dy minus d by dx, df by dy prime, integrated over x, multiplied times dy. So here I have a sum of n terms. I have the case, the I equals 1 term times delta y1 plus the I equals 2 term times delta y2 plus the I equals 3 term times delta y3, and so on and so forth. And in order to minimize I with respect to all of the yi's as a function of x, I need to set each of those terms there, multiplying the delta yi's equal to 0. So in particular, the functional I will be minimized only if the yi of x obey the equation df, I should use a partial there, df by dy minus d by dx, df by dy prime is equal to 0 for all I. And as above, the quantity appearing on the left-hand side of this equation has a name. It is the functional derivative of I with respect to yi. So whereas in the n equals 1 case above, the functional was minimized if y obeyed a single differential equation. Here, with n variables, the functional is minimized if if the yi's solve n differential equations. So perhaps I should stop there, but before I do so, are there any questions? Yes?
I'm sort of wondering if is this useful, or is it just a conceptual thing?
It is useful. It is not. So the Lagrangian formulation is a incredibly technically useful thing. I probably even already convinced you of that last class. The action principle, as distinct from the Lagrangian formulation, is not in and of itself terribly practically useful. But there are many things that are very easy to see, and in fact completely obvious in the action formulation that are sort of obscure in other formulations. So at this point, this is more conceptual than it is practically useful. But throughout the semester, we will find practical uses for this. And in quantum mechanics, it's incredibly useful. Other questions? Did I end at the right time today? Yes, I did end at the right time today. Good.